Let's see what the graph of an exponential function looks like in a very broad sense. So whenever we have a totally unfamiliar function and we want to get an idea of what its graph looks like, we start by just plotting a bunch of points and seeing what sort of shape they make. So I'm just going to take a whole bunch of values of x, -3 up to 3, and I'm going to punch them into my calculator and see what is 2 to the x. So 2 to the -3 is 1/8. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. And 2 to the 3 is 8. And I notice that every time I go down a row in this table, I'm multiplying by 2, which is exactly what I would expect because I'm taking 2 to a power. So every time the power goes up by 1, I'm going to multiply by 2. So let's see, how should I graph this? I could draw my axes so that I have a tick mark every 1/8, but then to go all the way up to 8, I would have to draw a really huge graph. So I think I'm just going to count by ones. But I notice that my y values are all positive numbers. And that's to be expected, right? Because I'm always going to get a positive number if I take a power of 2. So I think that my y-axis doesn't need to go into negative numbers. And I'm going to just draw my y-axis in the middle and my x-axis at the bottom. So then my x-axis, I'll have 1, 2, 3, 4, and -1, 2, 3, 4, and then 2, 4, 6, 8. Okay. And because my y values get really big, I really wanted to draw that x-axis down low so that I didn't have to waste a bunch of space, so I could actually get those big y values. So now I'm going to go through and plot my points. And these ones are easy to plot. So I've got 0, 1, 1, 2, 2, 4, 3, 8. And then over here, these are a little bit harder to plot. But a half I can draw, right? That's just halfway between 0 and 1. And then a quarter is going to be halfway between 0 and 1/2. Then an 1/8 is just going to be real small. And my graph looks something like this, just kind of filling in a smooth curve through these points. But we've got something happening here. As x gets more and more negative, I keep dividing by 2, right? So I keep getting smaller and smaller positive numbers, but I never quite get down to 0. And the way I indicate that is by drawing this red dashed line right at 0. In the graph, that shows that the graph gets close to this line, but never quite crosses it. So let's see what we see in this graph. So certainly any number I put in for x, I can take 2 to that power. The domain is all real numbers. If you absolutely love interval notation, you could say -infinity all the way to infinity. The range, well, we can get as small a positive number as we like, but we'll never get quite down to 0. So the range is just positive numbers, which we could write in interval notation as 0 to infinity. We can also talk about the end behavior, like we did for the power functions and the polynomials. When x gets very, very large, so when x is a large positive number, f of x is also a very large positive number. But when x is a very, very large negative number, we don't get negative values of f of x. In fact, when x is a very, very large negative number, we get as close as we'd like to 0. We don't get very, very negative. We get very close to 0. And that's what's shown by that red dashed line in the graph. That red dashed line shows that the graph gets close to 0 but never touches it. A line like that the graph gets close to but never quite rests on, is called an asymptote. This is a horizontal asymptote, and it's a horizontal line whose equation is y equals 0. So I did this for 2. If I did this for 3, I would see exactly the same shape, except that instead of counting 1, 2, 4, I would count 1, 3, 9. We'll see a shape that looks exactly like this, except maybe more stretched out, as long as b is greater than 1. So what does it look like then if instead of being greater than 1, b is less than 1? That's what we'll see in the next video.